Now let's continue with our mathematical derivation of the fast inverse square root algorithm. So we're going to start off with our value of x. So this is our decimal value. And our value of x is given by 2 to the e times 1 plus m. So if you like, the left hand side is the decimal value and the right hand side is the floating point representation. So we know that the 2 to the e gives us the range of values. So for example, our number will be in the range 1 to 2, 2 to 4, 4 to 8, 8 to 16, so on and so forth. The precision within the range is given by the mantissa, and that's the value 1 plus m. So it tells us whereabouts within the range our number actually exists. Now we're going to take the logarithm of both sides. So we'll take log to the base 2 of x, and this side here will be log to the base 2 of 2 to the e 1 plus m. Now it will become apparent as we work our way through why we're doing this. So 2 to the power of e and log to the base 2 are inverses. So this is just going to give us the value of e. Also, whenever we multiply this 2 to the e and the 1 plus m, well, multiplication within log is the same as addition. So this is going to give us log to the base 2, 1 plus m. So this line here is just equivalent to this line here mathematically. Now, the interesting section is really here. What we're going to do is we're going to take an approximation of this log to the base 2, 1 plus m. So the approximation of log to the base 2, 1 plus m is approximately equal to the value of m. So in effect, we're taking a linear approximation of this little function. So it means that the log to the base 2 of x can be written as e plus m. Now the thing to note here is that although we're taking this approximation, the actual Taylor series expansion of this function here is 1 upon ln2 m minus m squared upon 2 plus m cubed upon 3 minus m to the 4 upon 4. And if we were to take just the first term of this, which in effect is what we're doing here, we would take this term m divided by ln2. But we're not going to do that. We're just going to take an even simpler approximation, which is just the value of m. So if we wanted to, we could generate, rather than generate this equation here, we could generate higher order terms using the higher order Taylor series expansions here. But we don't want to do that, because all we're trying to do in essence is generate as simple mathematics as we possibly can. By simple mathematics, we mean mathematics that can be easily generated on a digital computer. So we don't really want to have terms of squares and cubes and divisions. We really just want to have multiplications and additions. So this is the reason why we choose just to represent log to the base 2 of x, log to the base 2 1 plus m as approximately equal to that value of m. So let's have a quick look at it in a actual graphical calculator just to see how close this approximation actually is. So the graph that we have here is our log to the base 2 1 plus m. Okay, I've used the value x here because it allows us to actually draw the function. So you can see this is log to the base 2 1 plus x. Now we're interested in our linear approximation to this. So rather than having the function here 1 plus x, we're saying that this is approximately equal to just the value of x. Okay, so we're saying it's approximately equal to this line here. So you can see here that it is approximately equal to it up until the value of 1, and then it starts to go off. But remember, our value for our m only ever adds up to a value which is between just greater than 0 and a value of 1. Okay, so it's going to be 1 upon 0 point, 1 upon 2, 1 upon 4, 1 upon 8, 1 upon 16, 1 upon 32, and when we add all those up, it never gets any higher than a value of 1. So this is the approximation that we are making whenever we use our log to the base 2 1 plus m is approximately equal to m. Now if we wanted to, we could continue our approximation using the Taylor series expansion, which would look like this. So you can see here our approximation is an awful lot better, and it starts to tail off up at the high end here. But we could add more and more terms to make this approximation even better. But there's no point in doing this, as I've said previously, because we're introducing a lot of complication into our mathematics. So this is the approximation that we're going to stick with. So we have ended up with this log to the base 2 of x is approximately equal to e plus m. Now we can call this equation number 2. Now from the previous video, we derived this equation number 1, which is I of x is equal to L times e plus m plus b. So we can replace this e plus m here with log to the base 2 of x. So we're going to finish up with I of x is equal to L log to the base 2 of x plus b. Now where are we going with this? We're doing an awful lot of mathematics and it doesn't seem to be going anywhere. But in effect, we have actually reached the point which is the really interesting point here. We have an equation here, if we rewrite it in this form, which relates the value of x, which is our decimal number, with the value of our ix, which is the integer representation of our floating point number. So there is a relationship between these two quantities. Not only that, the relationship involves a log to the base 2 of x. So we can go from our digital number by taking log to the base 2 of x and scaling it by this factor L, and then shifting it by the factor L times b. So we can call this here equation number 3. So I've reiterated this down here. I've written I of x is log to the base 2 of x, which is scaled by L and shifted by this value LB. Now this is very important because whenever we started off in the first video, we had two numbers, a decimal number and the integer representation of the floating point number. And there was no connection between them. But now we have found a connection between them. And the connection between them is actually in a form that is really useful. So how is it useful and how does it give us the fast inverse square root? Well, we will finish this off in the next video, and all of the mathematics that we've done over the last two videos will be understood, and it'll be understood, you'll be able to understand why it gives us the fast inverse square root. So thank you for listening. I'll get you on the next video. Goodbye.